during Technology Day at MIMSpace last year, we have introduced the topic of satellite communication, and today we will be expanding on activities in MIMSpace and the general topic of satellite communication, particularly direct-to-device as well. Firstly, what is the direct-to-device? So direct-to-device are abbreviated in D2D, as D2D is basically a kind of communication system that enables the terminal of the communication system to directly communicate with the device. So in the past, we communicate to the device through the gateway, through the terminals that are in the form of cell towers or Wi-Fi routers, and during these operations, we need to install a lot of terminals to basically route and switches signals between one channel to another channel and funneling from the backhaul to the users. The upcoming system will enable the device to directly connect to the communication system. In this case particularly is the satellite communication with the D2D functionality. This will enable the satellite to directly communicate with the devices. This capability will reduce, not only reduce the cost that users need to incur, but also will address the additional functionality of remote area connectivity as well. The value that this satellite communication D2D will bring is particularly the remote area connectivity. So in the past, we may not have a connection when the users are in a very remote area on the mountains or in the ocean. But the satellite, in particular the low Earth orbit constellation system, they cover the entire world, most of the part at least. So the satellite will have the coverage over every users that are in a remote area outside of cellular tower coverage. An example use cases of this satellite communication D2D are, as I said, the direct to our smartphones. There are already some use cases, some examples set by Apple for SOS signaling. There are also some upcoming communication system that would enable the satellite to do a direct message via a satellite network as well. There are also other use cases like in the manufacturing area where we can place basically sensors or communication systems in machines or in Internet of Things, and these devices can then communicate directly with the network without having the needs for a user terminal or a terminal that would do the routing. So next is the difference between the D2D satellite communication direct to device and the global navigation satellite system GNSS, or in our case we would normally use GPS. The difference here is that the satellite communication is a two-way communication. So we not only try to communicate with the satellite, but also the satellite would communicate to us. And when we're talking about the GPS, we are talking about the navigation. So the signal that we receive is only for navigation purposes. We know the position, we know the velocity of ourselves, the user. But in the case of satellite communication, we can communicate with other types of information. So not only the positions and the velocity, but also other kinds of signals, other kinds of messages that you want to send. That enables a lot of functionalities to be used from the user's point of view. So the use cases of the satellite communication direct to device or D2D there are a lot of use cases possible, but two use cases that are upcoming in the future are not only the communication with our smartphones, but also for Internet of Things. So for connectivity with the smartphone, in the past there are examples set with Apple for a SOS messaging. In the future, there are possibilities of communicating of other kinds of messaging as well. So we can make a message with our smartphones anywhere in the world where we already connected to the satellites, low Earth orbit systems. Another use case, which is Internet of Things, are that we can use the satellite broadband communications, this spectrum, to communicate with the devices on the ground, particularly where the backhauling or where the system backhauling the communications are not readily available, where this infrastructure would be deemed infeasible to be installed. Regarding the capital expense that may be limited there. So basically this allows a rapid deployment, not only for remote area but also where in any area that has a downed infrastructure. So for example, there might be an earthquake or some kind of natural disaster that disable the connectivity, the cell towers that we use nowadays. But law enforcement or the government agencies can rapidly deploy these satellite direct-to-device systems so that the government can communicate directly with any agencies across the nation, but also across the world. So the difference between communication with user terminals and with the gateway is that the type of message that we want to send or receive. Basically for user terminals, we are talking about the actual use cases that we want to use the connectivity for. We may want to use this user terminal to communicate our messages to our loved ones or our colleagues that we are working far away. But in the case of gateway, most of the time we are communicating all of this message from multiple users or from the satellite itself to the core system of the satellites. In this case, maybe the low Earth orbit satellites. So imagine you are sitting on the ground and you have a user terminal. You are sending messages or sending information via this user terminal through the router up to the satellite. And these satellites gather a lot of signals from a lot of users in your particular coverage area. And the satellite then downlink all of the messages in bulk to a gateway and connect that gateway to an internet infrastructure so that the satellite is not required to connect to each of the satellite internet infrastructure for each of the user. That reduces the cost of the system down a lot and also simplify the operations of the system. There are nonetheless many types of satellite communication from TMTC, which is telemetry and telecommand. This is for the operators of the satellite to communicate directly with the satellite to operate the satellite and the constellation system. There are also a payload communication with particularly Earth observation satellites. This use case only downlink most of the time the images that satellites are taking or the senses that the satellites use their onboard instrument to collect. So for the last question is the satellite communication as comparison to terrestrial system. When we're talking about satellite communication, particularly the very distinct characteristic is the coverage, because when we want to cover a certain area with a cell tower, we need to install these fixed cell towers at every point that may have a blockage or have a limited sight from the coverage of the adjacent cell towers. But in the case of satellite communication, every satellite contributes to the coverage of the whole world and basically incur the number of the satellites that may need to be in place at the first place. But this reduce the overall complexity of the operations by reducing the stress that the system may have. So the operators can operate the entire world when the system is operational. In the case of terrestrial network, you have to go directly to the area that you want to operate to allow the users to use that connectivity system to connect to the internet or to connect to any point of the network. But in the case of satellite communication, this will simplify the operations from the user point of view, that the user terminals, the things that we hold in hand, either it's going to be a big user terminals or devices that we use on the ground, they can be mobile and they can be dynamically allocated across the globe, and that simplifies from the user point of view the operations. The downside, however, the satellite communication is that currently, and this is because the physical characteristics of the satellite communications that we place the satellites, and basically this orbiting cell towers hundreds of kilometers above the sky. This increased the attenuation, so it increased the loss from the signal that the satellite communicates with the users. That means that we need to place a very powerful cell towers in space, and also the signals may not be as strong as the ones that we have here on Earth. But this cost is being optimized from the user's point of view on the coverage that allows the users to be more mobile and be able to move anywhere in the world. So that is the overall, the overall of the satellite communication, particularly on the direct-to-device or D2D. But we also want to introduce the activities here at MuSpace that related to that satellite communication as well.
So I would say under developing portfolio, the company direction is to engage in the satellite communication market as an equipment manufacturer. So we have been starting at the design and develop like the commercial of the shell product in the part of the communication, like the X-band patch antenna, X-band transceiver, and the X-band transmitter. But we not just limit for this of the product, we still need to be able to respond to the market that providing the broadband internet service by the satellite constellation. So we have set like a series of the RF equipment portfolio, including the phase array antenna, the user terminal for both fixed and mobility type, and the space terminal, as well as cover to the gateway equipment. And by doing this to support all of this product, we are working on develop the platform to perform the performance of our antenna technology and the implement to the digital signal processing technique. As we have performed the first demonstration on the last tech day, we have used the system testing kit with our S-band patch antenna to perform the RF link test between the antenna and the ground station, and we have proved that we can also able to handle the DVB-S2, which is the protocol for the digital video broadcasting. And for now and for the next step, we are preparing to perform the demonstration of the phase array antenna, that we can perform that the direction of the beam of the antenna to point to each of the direction for 3 baseline front end, like the KU band, KA band, and V band, or let's say around 15 GHz up to 52 GHz. For the communication payload, is typically consists of the antenna module, RF control module, the interface module, and the baseband module, or we call like a modem. We use all of these to integrate to support the transmission for both the data, voice, or video between the Earth and satellite. The common specific requirement for this communication payload, the main thing, important thing is the frequency band, which most of the player now try to up the converter to higher frequency, because in the higher frequency we can provide for the wider bandwidth, and it can support to the large amount of the data that we can transmit past to the specific frequency. It's also the reason that we as a mu space is also trying to play in the higher frequency, is up to around 52 gigahertz as well. Another requirement for the communication payload is for the capacity of the transponder, which must have enough to support the number of the communication channel and to support the high speed of the data rate of the data. And the payload itself must have a ability to perform the onboard processing, such as the channel multiplexing, the modulator, and the forward error correction. Apart from that, the important part is about the antenna. The antenna gain is the one of the parameter is also very important because this will a factor that affect to the EIRP performance and the signal strength as well as the signal to noise ratio. And because of the communication payload that we use currently is the phase array system, so the pointing accuracy is also important to acquire to be high precision to maintain the communication link between the payload to the ground.
So all of the equipment of the antenna is the integrated payload for satellite communication system. Basically, we need a bus system to operate this payload in space, which one of the primary requirements from the payload is that the satellite must point the payload to the right direction and maintain that pointing at a certain pointing accuracy. So attitude control is one of the major subsystems for the bus. Other than that, higher and higher frequency of a payload will require higher power because higher frequencies will consume a lot of power for conversion from intermediate frequencies. This means that the satellite must require higher power generation, which translated to more battery cells, more solar cells required on board the satellite. Overall, our system design dictates that the satellite, our satellites that we are developing will increase the size. Currently, we have a flagship for the B200, which is the 200 kilogram class of a satellite bus, but we also envisage that the satellite system is going for a 500 kilogram class as well, and that's the primary bus system that we will develop in the near future. Other than communications payload, there are other types of payloads that are applicable to the bus system as well that we will take into the consideration when we design the bus system, which are Earth observations, so telescopes or cameras that users want to put on board the satellites when they are doing the operations so that they can do some surveillance of the space assets, and also for looking down on the Earth and seeing the ground assets as well. Other than the observation payloads, the telescopes, there are also other types of payloads that are used for tracking. AISB is some of the payload types that are very particularly very popular lately. This kind of device will be used for tracking assets on the ground that are both fixed and also that are dynamically moved. So MuSpace is also working with our partners for the satellite internet services to provide in Thailand and also in this region. The business verticals that this system will be particularly used are the public sector and government, manufacturing. There are also healthcare, retail and hospitality, and also other kinds of applications that are applicable as well, like utilities or transportations and warehousing. This LEO satellite internet will enable a lot of connectivities in remote areas and also for mobility as well, because there are many types of user terminals to be installed and used, from a small community Wi-Fi, very small user terminal, to a maritime that can be used in boats, in big naval vessels, as well as terminals that are applicable for business and Jedi crafts. And this system will allow the users to use internet anywhere in the world, and we will particularly deploy this system with our partners here in Thailand. Other than the satellite internet services, we are also working with our partners in developing broadband communication systems and the equipment that can be used during that operations, including the payloads and also the spacecraft itself. And other than the space segment, we're also working on the ground segment, which include the user terminals and also the operations of the spacecraft, so that we can operate many satellites at a particular time.
For Mu Space product, we have a variety of the satellite components such as the S-band patch antenna, which have two of the model, the standard model and the high gain model, but two of the models also provide the high performance. And we also have the reaction wheel, which is the component that used to control the altitude of the satellite, and the EPS, which is the electrical power system that used for supply the power to the satellite. And we also have the energy storage equipment for both the stationary and portable type.
So Mu Space is supplying satellite equipment, energy storage equipment, and also satellite internet services. So if anyone has any interest in demonstration or using our equipment and our services, please reach out to our social media, Mu Space Tech, or you can contact via info@muspacecorp.com as well. Thank you very much for watching our session, and we'll see you in the next one.